Hello and welcome back. So today I want to continue working on my LISN by actually performing some tests to see just how well it works. So my plan is to look at the tested unit side impedance, to look at insertion loss, to look at isolation between supply side and the measurement port, and finally to look at isolation between the two ports. So there's quite a lot to do. And if you're curious, then keep watching. Now, the first thing to do, as with any good measurement, is to talk about the test setup and to do a calibration run. So for today's experiments, I will be relying on a spectrum analyzer that has a tracking generator output. So this thing can work like a basic network analyzer and plot an amplitude signal based on the signal coming out of the tracking generator. So the calibration run is done by connecting the output to the input through a coax cable, but also interconnecting the grounds. And the main reason to do this is to figure out the initial output level of the signal generator. Now, inside the generator's output, we have a series 50 ohm impedance, and at the same time on the other side, on the radio frequency input, so the spectrum analyzer's input, we have another parallel 50 ohm resistance. So when we're performing any sort of measurements, the thing that we will be seeing is the value here on the input port. Now, considering this arrangement, we have a voltage divider built with the two 50 ohm resistors. So one of the important things that this calibration measurement will do is tell us exactly what voltage value is at the output, which will be double that of what's on the input port. And this will be critical to know to perform accurate measurements further on. Now, other than making pretty plots, this thing can also be used to output a CSV file. So to output a coma-separated value table with every single measurement point that can further be processed using a spreadsheet program. So now, by processing the measured data and, well, multiplying it by 2 because we have a divide by 2 resistor network, we can work out exactly what our generator output was. So exactly what was the value of the generator at every single frequency point. So now we have this red plot that we will be using in further measurements. So now the first measurement to perform is to see what is the impedance of the LISN on the tested unit side. So this will be the basic setup that I will be using. Onto my measurement port, I will be placing an external termination resistor, so a 50 ohm. Then on the unit side port, I will be connecting the output and the input port of the spectrum analyzer. So we will have a similar setup as before, just that we will have in parallel to this connection the LISN. And now there's two important measurements to perform here. On the supply side, on the one side we want to measure the open circuit impedance, and secondly the short circuit impedance. The idea behind this is that we don't want to see any sort of difference in the two cases. We want to make sure that regardless of what is on the supply side, so regardless of cable length and battery impedance, this does not affect what the tested unit sees. So in the frequency range of interest, we should have absolutely no difference between these two measurements. So now if we run the simulation and we look at what we see on the input port, and we'll go to a linear plot, well, we see hundreds of millivolts, but this is not really a useful information. But we can work out, based on the voltage on the output port and resistances, what the equivalent impedance of our LISN would be. So we have a nice formula, I already prepared it here, and if we plot this, then we get a much nicer graph. So we can see that after a few megahertz, so around 10, it starts to flatten out. We have almost 50 ohms. Now it's not exactly 50 because this impedance is given by our external termination, which is 50, but this is in parallel with the 1 kilo ohm internal resistance. So we will never really get 50 ohms. Then we have a drop off. This is caused by the impedance of the inductor and the capacitor, and then this goes to some very low value. Now if we also look at what we should be getting with the other circuit, so the one where the supply side is shorted, so again I have the formula prepared. And we can see that, well, there's not much of a difference above 100 kHz, so as expected in the frequency range of interest, they're both identical. We only see a difference below 100 kHz. So this is where the cabling and the battery will start to have an impact. But it's not something we should care about. So, in theory, the LISN should work just fine. Let's now just see how it works in practice. So, to perform the measurement, I took the two cables, interconnected them, and plugged them into the negative output of the LISN. The grounds are connected directly to the case of the LISN. I added the 50 ohm termination, and the reason why I went on the negative line is because I already have a switch that can allow my line to be connected directly to ground or to be floating. So now if we look at the measurement, it's not very useful at the moment, so I'll just save this. And now if I turn the switch, go for another sweep, looks basically the same. But to see the exact impedance value, we will now have to take all these values and process them in the spreadsheet. So I took all the measured data, both for the open circuit and the short circuit on the input side. Also took the values from the generator output that we previously measured. And well, after processing it using the formula, I created this plot. So what we can see here is the impedance in ohms in reference to measurement frequency. So we do see that we have a slight difference between open circuit and short circuit. It's just that it's not where we're expecting the difference to be. So for whatever reason, we can see a difference here above a few megahertz, but we don't really see a difference below 100 kilohertz, so it's okay, I guess. And now to see just how well this impedance matches what we're supposed to be getting for a 5 microhenry LISN, I found this nice website. So this is a manufacturer, Compower, who is, well, advertising their LISN, so these are commercial products. But the nice thing that's present here is that they're showing their LISN's impedance compared to the CISPIR 16 and 25 limits. So we can take this picture and just overlap it with our measurement. And if we do this, well, what we can see is that our measurement, which is barely visible here behind, is well between the limits. So especially above a few megahertz, it's right there in the middle. It has some variation, but we're far away from any limits. But we do see that below a few megahertz, the whole graph is shifted to the left side of the limits. So my measurement isn't going here in the middle as it's supposed to, as is the commercial product, but rather it's touching the leftmost limit. And what this is telling us is that my inductor has a bit more than 5 microhenry. Otherwise, the graph would be in the middle. So this might be because I have too many turns, or my diameter is a bit larger than I previously calculated. But anyway, the unit side impedance is within some expected limits, so it's a pretty decent LISN, at least from this point of view. So the next measurement involves measuring the insertion loss of the LISN. Or in other words, to see what's the difference between the signal that is present on the power line compared to what is present on the measurement board. So see what sort of attenuation the LISN brings to the measurement. And now this is done by basically calculating the ratio between what we're measuring and what is on the, well, power line. And now this isn't as easy as it sounds, because we don't know exactly what's on the power line. We know what's on the output of the signal generator, but that first passes through a 50 ohm resistor. So based on the previous measurements that we already performed, the exact value of the generator output and the impedance of the LISN, we can work out what the voltage is present on the LISN line. And we can take that and compare it to what we're measuring. So now if we just run this simulation to see what we should be expecting from this measurement, we see that it's not a perfectly flat line. So above a certain frequency it does become flat, but at lower frequencies it starts to drop down. And now this is perfectly normal, because the main parameter that influences this measurement is the impedance of our 100 nanofarad capacitor. So at high frequency, its equivalent impedance is very, very small, so we get almost no insertion loss, but at low frequencies, its impedance starts to increase, and become comparable to the 50 ohms of the measurement line. And now this is not really a problem, but it's important to perform this measurement so that we can take this graph and use it as a correction factor to any further measurements that will be done. So to perform an accurate measurement with an LISN, whatever you're measuring should be corrected based on this insertion loss. So this will be the test setup. So what I did here is I took the generator's output, connected it into the tested unit side port of the LISN, and then instead of the termination resistor, I added the cable that connects the measurement port to the spectrum analyzer's input. So this is where the 50 ohm impedance will be. And now if we look at the measurement, well, it doesn't look that useful at the moment. So let's see how it looks after it's processed using the spreadsheet program. So I took the data from the very first measurement of what's on the output of the generator. Then I took the input from the output impedance, and finally the values that we measured with this experiment to calculate the insertion loss. And well, I plotted it out in two different graphs. On the one side I have this logarithmic graph, and on the other side I have a decibel graph. And what we can see from these is that, well, I do have some sort of insertion loss. It's not perfectly flat, there's a bit of a wobble in this curve, but it's always above -1 decibels. So it's pretty flat. So throughout the entire range between 100 kHz and 110 MHz, it's roughly flat. So my 110 nF capacitor, and with the smaller capacitor in parallel, is doing quite a good job. So now let's move on to the next test. And this involves measuring input isolation. Or in other words, to measure how much of the noise present on the input actually passes through the LISN to the measurement port. And now if you're using an LISN supplied from a chemical battery, then this test isn't relevant because, well, your battery will not be noisy. But if you have a different sort of supply, so either you're using the main supply or you're using some sort of DC-DC converter which can have noise on the output, then it's important to measure just how well the LISN will be filtering noise coming from the input rather than coming from the tested unit. And to perform this measurement, it's basically the same thing as with measuring the insertion loss. We need to compare what's on the measurement port with what's on the input. And now this raises a problem. What's on the input port? I mean, we know what's on the output of the generator, but we still have this 50 ohm resistance in series. So the very first measurement to perform to be able to perform this measurement is to measure the input side impedance. Then we can calculate what the input side signal is, and finally, by measuring the value on the measurement port, we can calculate what the input isolation is. Now, just to get an idea of what we should be expecting, we should get a curve that looks something like this. So our LISN is a dual LC filter with an RC at the beginning, and its corner frequency is somewhere below 100 kHz, so the inductors are quite small. So we have a minimum attenuation of about -3 decibels at 26 kHz, but then this starts to increase to -10 at 100 kHz, -30 at 1 MHz, -66 at 10 MHz, and so on. So this filter should be really good at filtering high frequencies, and not so good at filtering low frequencies. So now let's see what the actual device does. So first thing to measure is the supply side impedance. And for this, I took both channels, connected them together, so signal line to the input port, and then ground to the casing. And of course, I added the termination resistor onto the measurement port. And now, well, you can barely make it out from this picture, but we're working with very, very small signal values. This is something to keep in mind, because if you're working with very small values, well, there's a good chance of error in the measurement. But anyway, let's move on to the next test, which involves measuring the isolation. And for that, I left the generator output connected to the supply input, and I took the termination resistor off, and I'm connecting the measurement port to the spectrum analyzer's input. And now, if we look at the values, we have even smaller values than before. Now, just to make sure that what we're measuring is actually accurate, there's one more important measurement to perform to see what the noise floor of the measurement is. So what are the actual smallest values we can actually measure? Because anything close to that is not an accurate measurement. So the last measurement involves disconnecting the signal input. So just letting the machine sweep without having any sort of input. And this will be the absolute smallest signal that, well, we should be able to measure. But now, to make sense of all the data, let's turn to the spreadsheet program. So now, the first result involves the input side impedance, and we can see that it's around 0.1 ohms up to 100 kilohertz, and then it slowly increases. So this initial region is mainly caused by cable resistance and capacitor ESR, and then it increases because of the parasitic inductances and the, well, inductors, up to a point of about 60 ohms. And now we can take this information and our open circuit measurement to get this plot. So what I have here is two curves. In red, our noise floor, so what would have been the smallest value we could actually measure, and in blue, the value that we actually measured regarding the input side isolation. And what we can see is that, well, up until 100, 200 kilohertz, we can't really make out the value because it's, well, in the noise floor, so it's either this or something smaller. But after that, we can see that the two graphs are slowly splitting apart. So we can see that at about 1 megahertz, we have minus 40 decibels of filtration. At 10 megahertz, we have minus 60. So these are very close values to what we saw in the simulation. So the LISN is doing quite a decent job of filtering the noise coming from the input side. So now there's one last thing to test out. And that's to see just how well the LISN prevents noise from one line going on to the other. So because I wanted to put both my LISNs in the same box, one of the things you don't want is to have any sort of crosstalk in between the signal lines. And that is something that needs to be measured. So the setup will look something like this. I'm going to be injecting signal into one of the LISN ports, which will have a 50 ohm termination on the measurement port, and on the other line, I'm just going to be connecting the measurement port to the spectrum analyzer. And well, we should be getting nothing, but if we do get something, then we need to assess just how bad it is. So for this setup, I have the signal generator connected to the yellow channel with the 50 ohm termination resistor on the measurement port, and then on the black channel on the left side, I have no input. I just have the measurement port connected to the spectrum analyzer's input. And well, again, we have a nice curve. It's quite small, flat, I don't know, it looks nice. And again, to see what this curve means, if it's good or bad, we need to turn to the spreadsheet program. So now, taking information from previous measurements, like the initial signal level of the generator, the output impedance of the LISN, but also the measurements we performed, I managed to create these graphs. So what I have here is, in red, the noise floor, so the minimum signal level that I can measure, and then in blue, we have the level of the crosstalked signal. And what's interesting is that, well, the two overlap up until 100 kilohertz, so we don't know what the crosstalk is before 100 kilohertz, but afterwards, the two lines start to split apart, so we have a lobe going on the blue line, which falls into the noise floor again at around 7-8 megahertz, and then it rises back up. So there is a bit of crosstalk in between the two signal lines. It's in the minus 60 decibel range, but it's there, and it can cause problems. Now, it's been pointed out by the viewers in the previous video that my magnetic shielding isn't that great, so my two inductors have this magnetic shield going on them, and it's not the best thing ever, and well, the measurement confirms that. But the thing is that because of the shape of this measurement, so we have the two lobes, it's not just the magnetic shielding that's the problem. There's something else in there. And to look at that in more detail will be a topic for a different time. But for now, The LISN works, it works pretty well, so based on the measurements it's a pretty decent device, and it will be useful for future topics. But for now, hope you got some useful information out of this. Leave your thoughts in the comments, thank you for watching, make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.